Cylindrical capacitor. A thin-walled, hollow, conducting cylinder with radius r sub b is concentric with a solid conducting cylinder with radius r sub a less than r sub b. Each has length capital L. The two cylinders are attached by conducting wires to the terminals of a battery that supplies potential V. A solid cylindrical shell with inner radius r sub a and outer radius capital R less than r sub b, made of a material with dielectric constant kappa, slides between the conducting cylinders as shown in figure. So we have a solid cylinder here and the spherical shell, hollow cylinder, and in between we insert this spherical shell with radius capital R, outer radius capital R, inner radius R sub a. So this is inserted to a distance x, and as you can see there is also air remaining in between the spherical shell and the outer walls of the hollow cylinder. By changing the insertion distance x, we can alter the capacitance seen by the battery and therefore alter the amount of charge stored in this device. So we can change the capacitance seen by the battery by manipulating the distance, that the insertion distance for this spherical shell with dielectric constant kappa. Part A, determine the capacitance as a function of x. So that's what we will do in this video. So here is our hollow cylinder. It has this conducting solid cylinder inside, which has radius r sub a. And then we are inserting this dielectric with radius capital R. Because it's a shell, the inner radius is r sub a, the outer radius is capital R, but capital R is less than r sub b, so there is also air remaining here, and it's inserted to a distance x. And we're applying a potential between the inner solid cylinder and the outside hollow cylinder, outside walls of the hollow cylinder, as you can see here. Our first task is to calculate the electric field outside a cylindrical shell. So to do this, let's consider this cylinder, hollow cylinder, which contains charges at its at the outer surface. And to calculate the electric field due to these charges, I need to consider a Gaussian surface. So I take a Gaussian cylinder with radius r and length L prime. Now the cylinder of interest has radius capital R and length L, and it has uniformly distributed charge over all of its outer surface. So we're going to apply Gauss law. The first thing I note is that because this cylinder has uniform charge distribution, the electric field lines are radially outward, and therefore they will be parallel to the area vector defined by the outer surface of this Gaussian cylinder. So I'm going to write Gauss law. Closed surface integral electric field dot product with the area vector dA. This is going to be E times 2 pi r L prime. Why? Because the surface area of this Gaussian cylinder will be 2 pi r multiplied by the height of the cylinder L prime. This, according to Gauss law, is equal to the charge enclosed divided by epsilon 0. So this is Q in divided by epsilon 0. Now the question is, how much is the charge enclosed by this Gaussian cylinder? It is the surface charge density sigma multiplied with the surface area of this portion of the cylinder, which is 2 pi capital R L prime. divided by epsilon 0. So why is it 2 pi capital R L prime? Because the charge that we are enclosing here is basically for this portion of the hollow cylinder, and those charges are defined by the surface charge density sigma, which will be Q divided by 2 pi R capital L, the length of this cylinder, multiplied with this surface area of this portion, which is 2 pi capital R L prime. So it is the surface charge density, which is the total charge Q divided by the total surface area 2 pi R capital L, and multiplied by the area of the portion enclosed by the Gaussian cylinder 2 pi capital R L prime over epsilon 0. Now you can see that these 2 pi capital R's will cancel, and we will be left with QL prime over epsilon 0, but at the same time this is equal to E times 2 pi RL prime. So you can see that we will have a cancellation of these L primes, so these L primes will disappear. So we will see these L primes disappear, and therefore I will find the electric field to be electric field magnitude is Q divided by 2 pi epsilon 0 R. So 2 pi R comes from this portion. So at a radial distance r from the center, the electric field is the total charge of the hollow cylinder divided by 2 pi epsilon 0 R. Now let's go from this to a spherical shell. Now if I have inner radius r sub a and outer radius r sub b, the potential difference VB minus VA is minus the integral from RA to RB electric field dot product with displacement. Okay, so this is going to be minus the integral from R sub A to R sub B. What is the electric field between R sub A and R sub B? It is the electric field due to this solid, due to this spherical hollow cylinder, the cylindrical surface which has nothing in it, so it's a hollow cylinder. Why does this hollow cylinder represent this conducting surface? Because all the charges are at the surface of this solid cylinder in order to cancel the electric field inside. Remember, inside a conductor, the electric field is 0. So here, inside the conductor, the electric field is 0 inside. Okay, so that means all the charges reside on the surface. So that's basically what we have considered here. Now we're looking at this with respect to the outer hollow cylinder. So we have a surface charge here building on this solid cylinder, and then we have charge on this hollow cylinder outside surface. So the potential difference, potential of B with respect to A is minus the integral R sub A to R sub B. The electric field, according to, due to the inside solid cylinder is 2 pi epsilon 0. There is an L here that we have forgotten. because there's an L at the bottom, 2 pi epsilon 0 L. So capital Q over 2 pi epsilon 0 L times 1 over R. Because the electric field and displacement are in the same direction, we simply write dr. This is the integral of dr over r, that's natural logarithm of r, q over 2 pi epsilon 0 capital L, natural logarithm of r sub b minus natural logarithm of r sub a now we went from A to B. Now assuming that the outer surface is at the positive potential and the inner surface is at the negative potential, VBA should be positive. So you can see here in this arrangement, I will have the electric field pointing towards the center, not in the radially outward direction. That's simply because the outside cylinder is positively charged, the inside cylinder is negatively charged. In that case, this dot product will actually give me a minus sign, so this will become plus. So that is because VB greater than VA, electric field in minus r hat direction. Right, so this is negatively charged, this is positively charged. Electric field here is pointing towards the center. So in that case, I will have this as the answer for the potential difference, and that can be rewritten as V is equal to capital Q over 2 pi epsilon 0 L natural logarithm of r sub b divided by r sub a. So that's the potential. Now, how much is the capacitance? The total charge Q is equal to the potential difference V multiplied by capacitance. So we see that the capacitance is Q divided by V. So capacitance turns out to be Q divided by V, which is equal to 2 pi epsilon 0 L, 2 pi epsilon 0 L divided by natural logarithm of r sub b divided by r sub a. Okay. Now, so this is the capacitance normally we have between a solid cylinder and a solid conducting cylinder and an outside hollow cylinder, both conductors carrying surface charges. This positive surface charges on the outside cylinder, negative charges on the inside cylinder. Now, we need to consider this scenario of inserting the dielectric. The portion with a length of L minus x, because we only inserted a distance x here, L minus x, we will have the same scenario. It is filled with air. So what we will find is that we have capacitance without a dielectric between two cylindrical surfaces, 2 pi epsilon 0, but the length of this cylinder is not L, it is L minus x divided by natural logarithm of r sub b divided by r sub a. So that's basically the capacitance of that portion. Now consider the portion with length x. Okay, so that part is basically this part here. And if I look at the top view, I can see that there is the solid cylinder here. in the middle, the dielectric, and then from from capital R to R sub B, it's filled with air. Now, what is the capacitance C A capital R? That is the capacitance defined by this solid conducting cylinder in the middle, at the center, and this dielectric at a radial distance, capital R, from the center. So basically, I'm assuming that I insert an infinitesimally thick conductor here to determine the capacitance. Remember, that doesn't change the answer. So what is the capacitance between this that would develop between these charges and these charges? So that is the capacitance 2 pi. It was 2 pi epsilon 0. Now it is 2 pi kappa epsilon 0 because I have a dielectric. The length of this cylinder, it's the length of this cylinder, is x. So 2 pi kappa epsilon 0 x divided by natural logarithm. It was RB over RA. So the outside radius capital R divided by inside radius R sub A. That's the capacitance. How about the capacitance between the dielectric and the outside hollow cylinder surface? That's the capacitance in between these two conductors, this conductor and this conductor. And that is basically 2 pi epsilon 0 x, because there's no dielectric there, 2 pi epsilon 0 x, but this is in between an inner radius capital R, outer radius R sub B. Okay, and if you look at the potential difference between this point and this point, these two potentials, the potential of B with respect to A is due to the potential of B with respect to capital R, potential with respect to this surface, and potential of this surface with respect to this surface, plus V R sub A. Remember that the potential inside this conducting solid here is basically equal to 0, or it's a constant. A metal is an equipotential surface. There is no electric field inside. V is equal to a constant. So this is basically V in. Let me note that here also. V in is constant because the derivative of a constant is 0. That's what it means. Okay, so the voltages add up. So since the voltages across the terminals of these capacitors add up, we can see that these two capacitors, CAR and C capital RB, are connected in series. So in that case, they will have an equivalent capacitance 1 over C equivalent 1 is 1 over CAR plus 1 over C capital RB. So that will be natural logarithm of capital R over R sub A divided by 2 pi kappa epsilon 0 x plus natural logarithm of R sub B over capital R divided by 2 pi epsilon 0 x. But let's make this 2 pi kappa epsilon 0 x by multiplying also the top with kappa. So this tells me that the equivalent capacitance of this configuration for only the length, the portion with length x, is 2 pi kappa epsilon 0 x divided by natural logarithm capital R over R sub a plus kappa times natural logarithm RB over capital R. Okay, so this equivalent capacitance that we see here due to this AR and RB, so C equivalent 1 replaced by C equivalent 1, is actually connected in parallel with this capacitance defined by the solid cylinder and the air filled in between the solid cylinder and outside hollow cylinder, so this portion. Why? Because the two terminals of C equivalent 1 and C0 are the same. They're connected to the same potential difference. So I see that since C0 and C equivalent 1 have the same potential difference, across their terminals, they must be connected in parallel. So they are connected in parallel. And what is the total capacitance then? The total capacitance will be C0 plus C equivalent 1. In parallel connection, the capacitances add up. So I see that the total capacitance is C0, which is 2 pi epsilon 0 L minus x over natural logarithm R sub b over R sub a plus the equivalent capacitance that I have found up here, this equivalent capacitance, 2 pi kappa epsilon 0 x divided by natural logarithm of capital R over R sub a plus kappa natural logarithm R sub b over capital R. And that's the answer to part A of this question. So we have a hollow cylinder, nothing inside, which has radius R sub b. It's a conducting cylinder. So this surface is conducting, nothing inside. We put inside a solid conducting cylinder. It's filled with material. Inside the electric field is zero, potential is constant. It has radius R sub a. Now in between these two, we insert a dielectric with radius capital R, radius between capital R and R sub a, and that capital R is less than R sub b, so there's also part of it filled with air. Only a distance x into this cylinder. I assume that the outside surface is at a positive potential, the solid cylinder is at a negative potential, so I have positive charges outside, negative charges inside at the surface of this solid cylinder. So first task is calculate the electric field outside a cylindrical shell. So if you have a cylindrical shell which only has charges at its outside surface, we will see part of that charge due to this Gaussian cylinder, which has length L prime. The closed surface integral E dot dA, because I'm assuming this part has positive charge, electric field is radially outward, the area vector is radially outward, so they are parallel. So E times the area of this Gaussian cylinder, which is 2 pi r capital L prime. E times 2 pi r capital L prime. That's charge enclosed divided by epsilon 0. How much is the charge enclosed? The surface charge density multiplied by the area of this hollow cylinder enclosed by outside area enclosed by this Gaussian surface. This is 2 pi capital R L prime, the area. So the total charge it has is a capital Q sigma times 2 pi r capital R L prime over epsilon 0, where sigma, the uniform surface charge density, is Q total charge divided by 2 pi capital R L. That's the charge distributed over all of its outside surface, multiplied by 2 pi r capital L prime over epsilon 0. I find the electric field magnitude to be Q pi over 2 pi epsilon 0 L times R. So there's a 1 over R here. 1 over 2 pi R epsilon 0. So that goes here. And there is also capital L. So if the inner radius is R sub A, our outer radius is R sub B, if I'm considering the electric field due to this configuration, the potential difference between B and A, so I have VB minus VA, that's minus the path integral RA to RB E dot dr. In this case, I have positive charges outside, negative charges inside. Electric field is radially inward, so E dot dr is negative, so this turns into positive R sub A to R sub B integral Q over 2 pi epsilon 0 L 1 over R, the electric field in between these two. That's the electric field created by this solid cylinder, or that develops between this solid cylinder and the outside surface, and this electric field Q over 2 pi epsilon 0 L times 1 over R dr, electric field dot product with the displacement, integral from RA to RB, gives me the potential difference Q over 2 pi epsilon 0 L, natural logarithm of RB over RA. Okay, so we have the potential difference between two points in the radial axis between R sub A and R sub B, and that is basically defined by the electric field created by this solid cylindrical shell. Okay, the electric field inside is equal to 0, remember, and if you just consider the electric field created by the outside surface, it's basically the electric field that you would see inside this region here. And the electric field inside this region is basically equal to 0 because it's inside the solid conductor. Okay, so this potential difference VB minus VA is given by this. The charge Q is equal to voltage times the capacitance, so C is Q over B, 2 pi epsilon 0 L over natural logarithm RB over RA. The portion with length L minus X is filled with air, so this part is filled with air, so it is 2 pi epsilon 0 L minus X over natural logarithm RB over RA. And the portion with length X is filled with dielectric to some extent to a radial distance capital R, and after that it's filled with air. So for CAR, I insert an infinitesimally thick conducting surface for this portion in order to calculate the capacitance, and I know that that doesn't change the answer for the overall capacitance. So this is going to give me CAR is 2 pi kappa epsilon 0 X over natural logarithm capital R over RA, and for CRB it's going to be 2 pi epsilon 0 X natural logarithm of RB divided by capital R. Since the voltages add up here between BR and RA, because the voltage is defined with respect to the outer surface and inner surface, inner cylinder, they are connected in series, and these are connected in parallel to this capacitor that develops between this surface and this surface for the length L minus x. So this portion has length L minus x. So this is L minus x. All right, so for that portion, I have the equivalent capacitance defined by 2 in parallel with C0, and the capacitances, the reciprocals will add up for the reciprocal of equivalent capacitance in the series connection, and in parallel connection, the capacitances will add up to give me the final answer to part A of this question.